I hesitate to even do this because there are so many ways of accomplishing this fact. But at some point, you need to use the theorems or definitions that you know about a square, and at some point, you need to know what you know about a circle. So I am going to do my circle first. You can construct a square first. Absolutely, not a problem at all. You've got lots of options to do on this, but I'm going to go ahead and construct that first, and I'm going to draw a diagonal now, which is also the diameter. These 2 points I want to be the endpoints of my square, and so now what I need to do is to find the perpendicular bisector of this. So I need to open a little bit more than halfway. That's all that needs to occur. Oopsies. And then I draw in my perpendicular, which is here. And then this point here and this point here must be the endpoints of my square. Why? This is 90 degrees. These are all equal to each other. And so those are all of the theorems that are true about a square, making this a square. Again, so many different ways. Hesitate to even show you one because I don't want you to get locked into mine, but you have to think about what you know about a square in order to do that. So for number 3, again, tons of different ideas and options, but the one thing I know is that since it is a rectangle, I need to have 90 degrees somewhere. So I don't even, well, yeah, I do, especially for the 1 to 2. So I'm going to go ahead and construct a 90 degrees first. So for constructing a 90 degrees, it's perpendicular bisector. Oh no. That's better. I have confusion now. Oops. So this little one was not what I wanted. That was icky. So I have a perpendicular. Now, once I have a perpendicular, I need to do some measuring. So I just need it to be in a 1 to 2. So I'm going to measure from here to here. That'll be my 1. And then that will be my 2. Now, the other thing that I need to do is just go right up here. So that's now a 1 and that's a 1. And then open up the full amount of the 2. And then I've got my 2. So this point is my vertex that I'm looking for. And I go from there. Again, loads of ways, but I do need to make sure that I have a 1 to 2 ratio when I'm done, because that's what I asked you for. Alright, so then we're at a parallelogram. Again, tons of options of how it is that you are going to construct them. I like to be simplistic, so I'm going to go ahead and go with, let's just draw something parallel first. So, actually, I don't even think I'm going to do that. I'm not. I'm going to go ahead and go with the other part of some theorems. I know that whatever this is, I'm going to just randomly pick a point down here. It's a rhombus. I mean, it's a parallelogram, so it doesn't matter. And then I'm going to go ahead and mark up here. So I know that these 2 markings are equal to each other, and not the definition, but a theorem of a parallelogram enables me to go here and then here. So totally different method, using a theorem rather than a definition. Now, my other option that I could have done was I could have drawn a parallel using like corresponding, using the theorem, I'm not the theorem, but the definition, and then went ahead and marked off equal lengths here and here, and I could have done that there. So lots of different approaches that I could take, but that is definitely one of them. Okay, let's go ahead and look at number 5. So I want you to construct an equilateral triangle inscribed in a circle. So, there are actually lots of different options here, but I'm going to go ahead and start with a circle. You could actually start with an equilateral triangle. But I'm going to start with a circle, and with the circle I'm going to mark off 1 length. Now, what I'm using is that if I draw a hexagon in here, that's 6 equal sides. And then if I do connect every other, that's 3 equal sides. So that's what I'm going to do. So this is the length of my radius, which means it's also the length of my side. I've done this one for you before. And then we just check to make sure. Wow, that's pretty darn close, so that looks good. And so then this one, and this one is what I want to connect. So that will give me my nice little equilateral triangle inscribed in a circle. Again, inscribed means that each of the vertices has to actually touch the parts of the circle there. All right, looks good.